Before we go into details, we need to know that electrostatics is just a branch of science. Okay, branch of science that deals with the study of charges or charged particles. Okay, so from this branch of science, we know that like charges are having the same charges that are the same. Positive and positive, or negative and negative, those charges will repel. And then the unlike charges will attract each other. Okay? Like charges will attract each other. So this we need to know. Now, what if we have charges that are at rest? Okay? So if we have charges at rest, then there is a force that will be acting between those two charges. It can either be a force of attraction or a force of repulsion. So for charges at rest, we know that the force between them is what's called the electrostatic force. The electrostatic force. So what does this force do between the charges? So one thing we need to know and remember is that there's a German scientist known by the names of Coulomb that did a thorough study. What really happens when two charges are at rest and what sort of force works between them and what the relationship of force is, the charges and the distance between the charges themselves. So upon his conclusion, he said that this force is directly proportional to the magnitude of the charges, the Q1 times product of magnitude of the charges, not forces, and then it is inversely proportional to the square of the distance of separation. So it's just more like related with the universal law of gravitation for Newton, whereby you look at the force being directly proportional to the masses and inversely proportional to the distance of separation. But in this case, we're focusing on the charges. So if the proportionality symbol was to be eliminated, then K will have to be introduced, whereby F is representing the force, that is the distance of separation. These are the charges, and then K is what we call electrostatic constant. Okay, the constant of electrostatics, which is the same as 9 times 4 to the positive 9. Constant that we need to remember. So for any given two charges at a time, this formula will be used. So this formula brings about what we call Coulomb's law. Coulomb's law of electrostatics. Okay, so what does that law state? We are saying that the magnitude of the electrostatic force is the magnitude of the electrostatic force. Magnitude of the electrostatic force in between 2-point charges. In 2-point charges is directly proportional. Directly proportional. The product, okay, of the charges or magnitude of the charges, and inversely proportional. Inversely proportional, the square of the distance between them. to the square of the distance between the charges. Sometimes we even talk about the centers. Okay, so that is what the formula says. Force is directly proportional to Q1 times Q2 over R squared. So that is Coulomb's law. And we just need to know how we state that. So it's saying it's just similar to the universal where there is a G, and in this case, we just have K. Now, what if we have, let's say, we have an example. We have this as our sphere number 1, I'll call it A. And then this is sphere number 2, I'll name it as a B. And then let's say we have distance from the centers, I'll just say 15 millimeters. Okay? Just for convenience, what if I use this as a 6 MC? And then I can use this as a 12 micro with a C. Okay? And then I need to get the force, the electrostatic force between the two. So both of them are positives, it's fine. I have no problem with that. So we know that our Q1, let me call this Q1 and then let me label this as the Q2. So if that's the case, so this N usually represents what we call nano. And nano is times 10 to the negative 9. So the overall charge is going to be 6 times 10 to the negative 9. And then this symbol mu represents micro in electrostatics times 10 to the negative 6. So the charge here is 12 times 10 to the negative 6 coulombs. This distance needs to be converted to the standard unit in meters. So my force, if I use that formula, is going to be K, which is 9 times 10 to the 9. And then I'm multiplying by 6 times 10 to the negative 9. And then I'm multiplying by 12 times 10 to the negative 6. And then I'm dividing it by the distance. We said it was 15 millimeters. When you're changing or converting millimeters to meters, you usually divide by 1,000. Okay, so you can do that, or you can multiply by 10 to the negative 3, whichever one is easier. That's going to be 0,015. Then I'll square that. Okay, so when I put that into the calculator, times 2 to the negative 6, and then I'm dividing by 0,015 squared. That becomes just 4,13 joules. Okay, so that is the force that is existing between the two. Now, one thing we need to know is that that force is what A is having on B, and then it's the same force that B is having on A. In other words, it's more like Newton's law, Newton number 3. As in opposite and reaction will be equal, but opposite. So the force that A impacts on A impacts on B is the same as that B impacts on A in the opposite direction. So since the charges are the same, which means it's going to be repulsion that takes place. Okay, that is just a simple scenario. Now, what if we have, let's say, 3 bodies? Okay, something like this. And then maybe we're given a distance of 12, maybe you're given a distance of 16 with different charges. I call this A, B, and then C. Let me call this 8 microcoulombs. I'll call this 9 microcoulombs. And then maybe 16 microcoulombs. For this internal problem. Now, if it is 3 charges, what we normally look at is you might be asked for the net electrostatic force. Okay, net electrostatic force of, let's say, A, net electrostatic force on A as a result of B and then C. The net electrostatic force on A as a result of B and then C. Or we can say the net electrostatic force on B as a result of A and C. So in most cases, it's all about combining the two charges. Let me see how we can do this very fast. Okay, so since I'm looking for the net electrostatic force on A due to B and C, step number one, I need to get the force between A and B. Okay, so force A and B, remember we say QA times QB over the RAB squared. So when I do my substitution, that is 9 times 10 to the 9, then times 8, we said micro is 10 to the negative 6. And then this is 9 times 10 to the negative 6. Distance of separation is 12 centimeters, which will be 0.12 squared. And I convert that to meters. So that's a 9 times 8 times 9 times 10. I'm gonna put that negative, okay. And then we're saying this is 0.12 squared. Okay, so this gives me just 45 Newton. Okay. Now that is the force on A as a result of B. So since the charges are opposite, then there's going to be a charge. So it's moving to the left. Okay, then I need to find also the force between A and C. Force between A and C. So the formula, that is QA QC over RAC squared. So 9 times 10 to the 9, that is 10 to the negative 6. Then 10 times 10, that's gonna be to the negative 6. Now the distance we have in 12 and then 16. Okay, so 12 plus 16, that is 28. That's 0.28, but squared. When I put that into my machine, 9 times 8 times 60, okay, then I'm dividing by 0.28 squared. I'm having 16.53. Yeah, Newton. Now, since the charges are the same, this is a positive and then this is also positive, there's going to be repulsion. So that force is going to act to the right. Okay, so that is the right. Now, for me to get the net, I must get the F of AB plus the F of AC. I do the substitution. So if my left is a negative, then I'm going to have negative of 45 Newton plus 16.5. So negative of 45 plus 16.53, ending up with 28.47 Newtons to the left. Okay, so that will be the net electrostatic force if, let's say, I have 3 point charges. Then what if the point charges are just at an angle? Okay, an angle of, let's say, 90 degrees. Okay, let's say I have A here let's say I have another charge B, and then I have another charge that is C. Let's call the distance here, I don't know, let me call it a 2 meter. I'll call this a 3 meter, just to make it drop it easy. So I'm going to call this negative 3 nanocoulomb. I'll call this a positive 4 nanocoulomb, and then I'll call this positive 6 nanocoulomb. Okay. Now, if this is the case, and then they ask us to determine the net electrostatic force. Okay. Net electrostatic force on B to A and C. Okay. The net force on B as a result of A and C. Now, this represents what we call the 2D kind of electrostatics, whereby we have the horizontal as well as the vertical dimensions involved. So what we need to find the force that is acting within the vertical as well as the force that is within the horizontal. So this is F vertical, and then this is going to be F horizontal. So the net force for both needs to be found. So I'm going to get the force vertical. Remember we said AQA, QB over R squared. Force on B as a result of A. So if our A was a negative 3, that is 10 to the 9 times, we're saying 3 times 10 to the negative 9 because of the A. And then we are multiplying by 4 times 10 to the negative 9. Distance of separation is 2. I'll just square that. Okay. When I punch that into my calculator, having 9 times 3 times 4. Okay. Over that. This means 7 times 10 to the negative 9. That is newtons. But since the charges are opposite, there's going to be repulsion. So this is going to act downwards. And then let's look at the force horizontal. With the horizontal force, I'll be looking at QB times QC over R squared. 9 times 10 to the 9 times 4 times 10 to the negative 9 times 6 times 10 to the negative 9. I'm dividing it by 2 squared. Okay, so this is going to give me 24 times 10 to the negative 9. Now, since the charges are the same, it's going to be repulsion. So that is to the right. Is it to the left or to the right? Does it matter? It does. To the left and to the right. So that's going to be, remember, let's go back. Let's just go back a bit. Remember, there's going to be attraction. Force is up, it's acting downwards. So this is going to be up. Okay? And then this is going to be to the left. This force is in the, just focusing on B alone. Okay. Then now, if we look at the forces, so it's going to be something like this. Force vertical and then the force horizontal. So this is a 27 times 10 to the negative 9. We're saying this is 24 times 10 to the negative 9. We need to find our resultant. Okay. For us to find the resultant, we use the theorem of Pythagoras. R squared is equal to x squared plus y squared. F horizontal squared plus F vertical squared is equal to our F resultant squared. So 27 times 10 to the negative 9 squared plus 24 times 10 to the negative 9 but squared. So I'm going to find square root so that I have my F resultant. Okay, I need brackets here. Is 10 to the negative 9. And then I'll square it to 10 plus 24 brackets is times 10 to the negative 9, but also squared. Okay, I'm having a very small number. It is 1, 2, 3, 4, 5, 6, 7. So 3,612 times 10 to the negative 8 meters. So that is the net electrostatic. Now we also need to find the direction. So with the direction, you need to use the fig where we look at the angle of inclination, which is the arctan of the F vertical over the F horizontal. Okay, shift tan. Our vertical was 27 times 10 to the negative 9 over 24 times 10 to the negative 9. If I put this into my machine, I'm going to have, what am I having? 8,37 or 37 degrees. So that will represent our angle, and then that is our magnitude. All right, so that is if we are being asked to determine the electrostatic force or the net electric force. Then I just want us to look at what we call the electric field. Okay, so electric field is basically a region of space. A region of space where a charged body, sometimes it's a charged body, will experience force. At times we say it's a region of space in which an electric charge experiences a force. So the direction direction of the field at a point in space is the direction in which a positive one charge would move if it was placed. So direction that this force will be operating on that object is basically the direction that a positive one charge would take if it was placed within that region of space. Then we also have what we have electric field point. Okay, maybe let us try that also. Electric field, the point where we say is the force per unit positive charge is placed at the point. The force per unit positive charge placed at that point. We shall go in details when we look at some examples. Then we also need to remember how to represent, let's say, the electric fields. An example, if you're looking at an isolated positively charged sphere. So we know that the field lines must be moved out of the sphere. So normally use arrows in that sort of manner. What if it's negatively charged? Then the field lines should be seen just entering into the sphere. Okay. Now what if we have, let's say, two charged bodies. Remember we said positive and positive, there will be a repulsion. Okay. Now the technique with drawing this, the repulsion, we shall have, and then the field lines must not cross each other. Field lines must never cross path of each other. Must go in. So since they are positive, then the field lines seem just living, seem stored here. Then the magnitude sometimes will also determine how many field lines leave the sphere or enter into the sphere. Sphere with a bigger magnitude will have more field lines. Those with smaller magnitude will see few field lines. And then if it's negative and negative, so still it's going to be repulsion. Yeah. You must touch the sphere. As long as we see the correct pattern and correct format of the field line. So the arrows should be seen entering into the sphere for as long as they are negatively charged. Now this region of space, there will be no force for, because the net force there is 0. So sometimes, let's say if you're talking about the electric field, sometimes you can put a positive Q here or a negative Q there, and then see what will happen. Then what if the charges are opposite? That's when we say it, we shall look at the attraction. A positively charged or negatively charged, we should be able to see field lines that are leaving positive spheres and moving into negatively charged sphere. Leaving something like that. Doesn't matter how it looks like, as long as we see field lines leaving the positive and getting into the negatively charged. Now the formula for electric field, we know must be given as E is equal to F over Q, where E is electric field and then F will be that force at that point, and then Q will be the charge, magnitude charge. Now if let's say we were to focus on the electrostatic force between the electrostatic force between, let's say, the big Q and then the small positive Q. From the Coulomb's law, we know that that will be K times Q, then times a small q over the distance of separation. So if we do the substitution, it's going to be K, Q, that Q over R squared times Q. So this is going to cancel that out, and that leads us to this other formula which we normally use, is equal to KQ over R squared. So remember, the force due to the test charge. Okay? Due to the test charge. So that we need to remember as well. Then if let's say we want that force, we can just cross multiply that so that we get the times the magnitude of that charge. Then one other thing that I can probably say is that whenever we have, let's say, the net electrostatic force or the net electric field being 0, simply means the charges must be opposite, or the electric field have to be opposite in direction. Okay guys, that's a brief sort of start. Then let me just look at the examination guideline. So with the examination guideline, what is expected of us? Number one, we need to know how to state Coulomb's law, that the magnitude of electrostatic force exerted by one point charge on another is directly proportional to the magnitudes of the charges and inversely proportional to distance between them. To be able to solve problems using this equation, this Coulomb's law, that is for 1D, where the charges are placed in a single line. And then solve problems with a 2D, where we have a 90 degree somewhere, somehow. And then when we look at, let's say, the electric field, we need to be able to describe an electric field as a region of space in which an electric charge experiences force. The direction of the field at a point, the direction at a positive one charge. Okay, we need to be able to draw the field patterns for a single point charge. What if there are 2 point charges? What if they are charged spheres? Then we need to define electric field at a point being the electrostatic force experienced per unit positive charge placed at that point. We saw that. And then we should be able to use this formula, the E is equal to F over Q. Then solve problems with that formula. Then calculate the electric field at a point, the number of charges, and so on and so forth. Okay. So this is the examination guideline, and that is what exactly is expected of us. Then we need to look at some worked examples, so exam type questions. This is okay. Question number 1. I can start from question number 1. Next thing. All right. So question number 1 is telling us if we have 2 spheres, M and N. 2 spheres, M and N, on insulated tank M with a charge of negative 4 nanocoulomb, that is placed 8 millimeters away from A, is a point that is K, and so on and so forth. Then they are telling us that the net, in capital letters, the net electric field strength is acting east. So we don't know the magnitude of N, we only have E, so the E net, the 2 times 10 to the 5. This distance needs to be converted to meters. Okay. You know that that's negative 4 times 10 to the negative 9 coulombs. All right, let's see. So define the term electric field point. So we say this is the force that is experienced, okay, but per unit positive charge. Per unit positive charge placed at that point. Placed at point or placed at that point. Okay, that is if they ask you to define electric field at a point. That would be it. Then calculate the magnitude and direction of the electric field at P as a result of electric field at P as a result of electric field between P and M. So from our formula, we said E is equal to KQ over R squared. We know that K is 9 times 10 to the 9. Charge, we said it was negative 4, but you don't need the negative sign. Just magnitude, that is 4 times 10 to the negative 9. And then the distance of separation is 15 millimeters. Convert that to meters. So that's going to be 0,015 squared. Okay, when I put that into the machine, I'm getting 0.15 squared. I'm getting 1,000. Okay, 1,000 Newton per coulomb. Now, which direction is it? So they want the electric field at P, the result of P. So since we're taking this to be a positive one, and then there's a negative, there's going to be attraction. Okay, so the force at P is moving to the east or to the right. To the right. Then they want us to get the magnitude of the charge on N. Magnitude of the charge on N. So since we have the net electric field, I think we can use electric field. Then we can find the electric field at P as a result of N, which will be K, the Q of N over R squared. So that at the end we have our E net being the E as a result of M plus the E as a result of N. Something like that. So since we have the first one, we just need to play around with that. So I'm going to say 9 times 10 to the next equals 9 times the charge of N over the distance between P and N, 15 and 45, 0.05 squared. Okay, when I put that into my machine, 0.045 squared, having a very big piece. Just makes sense. 1, 2, 3, 4, 5, 6, 12. It's gonna make sense. It's gonna make sense for that's 12. I don't know. Let me just, okay, I'm having 4.44 times 10 to the 12 QN. Okay. So the net that side was 2 times 10 to the 5. So the net is 2 times 10 to the 5. We are saying this is equal to the 160,000 plus 4.44 times 10 to the 12 QL. Yeah. Okay. Now someone asked, why are we adding them? Now, since the net force or the net electric field is acting eastwards, which means all of the charges, all the electric fields must be in the direction. So we are moving this one in the east. So then I'll move this to that side. So 2 times 10 to the 5. Then I will subtract my 160 tau. My 160 tau, I'm getting 40 tau. Is equal to 4.44 times 10 to the positive 12 Qn. Divide by 4.44 times 10 to the 12. Divide by 4.44 times 10 to the 12. This cancels that. Remember, we said we're going to subtract when you transpose that. So Qn going to be 4.44 times 10 to 12. Okay, I'm having 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm having 9.01. And it's 10 to the negative 9 coulombs. Or someone can say that is 9 nanocoulomb. Now with the charge, it will be positive. Then 1.4 is charge on the sphere, positive or negative. Sure. Answer that. Positive And then they want us to sketch the net electric field pertaining to M and N. Now we said it's positive, and then the original, this one, was negative. So that is a positively charged and negatively charged attraction. Unlike charges attract each other. So, unlike charges must repel. Whereas the like charges, unlike charges must attract. Whereas like charges do the repulsion. Then calculate the magnitude of the electric force that an electron will experience when placed. Calculate the magnitude of the electric force. Guys, how do we go about that? Okay. So we know that E is equal to F over Q. E is equal to F over Q. And what did we say? We say that so I'm still on the same question. Yes. Okay, calculate the magnitude of electric force an electron. Okay, since we're focusing on an electron, would experience when placed at that point. So since we have the electric field, the net electric field, we just need to multiply. So Q times E, we know the charge of an electron is going to be the one of times 10 to the negative, as I need the electron charge with my formula. Okay, so I'll get my net, which was 2 times 10 to the 5. And then I'm just going to multiply it by the charge of electrons, which is 1,6. And just confirm. So saying electron charge. Okay. So it's saying it's 1,6 times 10 to the negative 9. Okay, so when I multiply to, you can put the negative sign, there's no problem. When I substitute that, 2 times 1.2, having 3,2 times 10 to the negative 8, it will be newtons. Guys, that will be it with that first question. Then my question number 2, they're telling me that the diagram below shows two spheres A having that much charge and sphere B insulated. Distance between them is that. And they want us to draw the field pattern. So a negative and a positive. You know what to do? Attraction. Attraction. So we just so field lines should be seen leaving. Field lines should be seen entering. What's wrong with me? This one lies. Okay, so say, say, like that. All right, then 2.2, calculate the magnitude and direction of the force exerted by B on sphere A. Okay, so from electrostatic force, we said F is A Q1 Q2 over R squared. That's 9 times 10 to the 9 The charge on A is 4,5. 10 to the negative 5. 4,5 times 10 to the negative 5. That is 9,5 times 10 to the negative 5. Distance of separation is 0,35. Okay, and then I'll square that. Putting this into the machine, I'm gonna have 9 times 10 to the 9. That's 4,5 for the multiplication. Okay, then we multiply by the 9,5 times 7, okay, that much, over 0,35 squared. Having 314,08. But since we're focusing on B on A, then the direction is going to be the right. B on A, the right. They give an attraction. Then calculate the strength of the electric field at P, the result of the strength at P. So we're gonna assume that instead of having the charge of P, just have a positive, because they're asking for the strength at P as a result of P. So that will be E is equal to KQ over R squared. 9 times 10 to the 9. And then we need the charge of A. So it was 4,5 times 10 to the negative 5 over the distance is still the same. Okay, so that's going to be 9 times 10 to the 9. Multiplying it by 4,5 times 10 to the negative 5 over 0,35 squared. Very short number. 3, 1, 2, 3, 4, 5. So I'll say 3,31 times 10 plus. Since electric field is Newton per Coulomb, also going back to the right. Okay, question number 3. Two identical spheres again, AP insulated and stands are placed the centers having 10 meters apart, as shown in the sketch. So the charge on A is negative 10 nanocoulomb, and then B carries some charge that we don't know. Then the net electric field that, so this is more like this question. Define electric field at a point. Remember we said electric field at a point is the force per unit positive charge that is placed at that particular point. I'm not going to write that. Then they want us to draw the field pattern A and B due to charges A and B. Now, since the net force is acting to the left, but it will be at this point, acting to the left. What do you think? What do you suggest? What do you think? So simply means that since it's negative charge and the net force is the left, so which means the force between this and it is also left. So which means it's more like an attraction force. Okay? That means I'm going to have a positive, then I have a negative. What that means? Attraction. Okay? That is attraction. And then they want us to get the magnitude of sphere B. So in that case, I'm going to use electric field. Okay, so I need to get the electric field between E and between A and P, and then the electric field between B and P. Then I use the net. Okay, so electric field of PA will be KQ over R squared. That's 9 times 10 to the 9. The Q we said was negative 10. Okay, I'm dividing by 2 centimeters, 0.0 squared. So put that into the machine. I'm having 9 times 10 over 0.02 squared. Having 337,500 Newton per coulomb. Then I'm having the E to be, which is EQ over R squared. That's 9 times 3 to the 9. That is the QB over 0.08 squared. Simplify that. Having 0.08 squared. Sure. Very big number. Scale. I'll count 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12. It's 1,4,1 times 10 to the 12. I'll call that cubic. Then now look at our inlet being the same as the EGA plus the EB. Now the net that they gave us was 3,943. 3,943 times 10 to the 5 is equal to 337,500 plus the 1,41 times 10 to the 12, but QB. So I need to take this aside using subtraction. Okay. So when I do that, I have 3,945 times 10 to the 5 minus 337,500, which gives me 5,000. It's 1,41 10 to the 12 cubing. Then divide both sides by 1,41 times 10 to the 12. That cancels that. Let's see, 1,41 times 10 to the 12. Sorry for rounding off in advance, but it will make just little difference. So the charge on B, I'm having 1, 2, 3, 4, 5, 7, 8. Okay, 4,04 times 10 to the negative 8. Guys, that's that. Then they're telling us that sphere B is removed. State whether the electric field at P due to the charge A will increase, decrease, or remain the same. So, since B is removed, it's having an effect on the net electric field at P. If it's removed, automatically it's going to decrease. Okay, then question number 4. Okay. They are telling us that 300 microcoulomb charges ABC, so it's space 0 centimeters on a straight line in a vacuum. Distances are 3 that and so on. Define electric field at a point. We said the region. Is this a region of space? No. Force by unit positive charge that is placed at that point. Point 1 answered. Then they want us to draw electric field lines associated with A only, since it's a positively charged sphere or object. Then the field lines should be seen moving out. So direction Let's sort straight lines, getting longer. 4.3, they want the magnitude of the electric field strength at position where B is and B2A on. So the electric field at this point B as a result of A. So if we place a positive 1 there, we shall ignore the charge of B. So that's going to be E being KQ over R squared. 9 times 10 to the 9, that's 100 times 10 to the negative. Distance 33 centimeters. 0.03 squared. So that's gonna be 9 times that over 0.03 squared. So that's gonna be 1, 2, 3, 4, 5, 6. That's some 39. So 1 times 10 to the 9. It's 10 per coulomb. Or you can write the whole billion there. Fine. Then Coulomb's law in what? Remember we said the electrostatic force. The electrostatic force, whether it's attraction or repulsion, between two charges. Between two charges is directly proportional. Directly proportional. The product of the charges, the product of the magnitude of the charges, and inversely proportional. Inversely proportional to the square of the distance between them. Distance between them. Okay, remember I said that it's if that is true, then they want us to get the net electrostatic force experienced by point charge P as a result of A. So they want the force because of B and because of A. Okay, so I'll just kind of really draw that for my convenience. What is this? Here's the 3 and the 4. Okay, so I need to get the force. I need to calculate the force in A and C. Okay, just for convenience. HA C over R squared. So 9 times 10 to the 9. That is 100 times 10 to the negative 6. 100 times 10 to the negative 6. Distance of separation is 3 and 3. It's 6. So that's going to be 0.06. That's it. Okay, put that into my machine. It's 10 to the 9. Multiplied by 100 times 100 like that over 0.0. Giving me 25,000. Okay, that is nothing. Since the two are positive charge, then let's consider. Since the 20,000, then I look at the first thing beyond. So Q over R squared is going to be more or less the same thing. So 100 times 10 to the negative 100 times 10 to the negative 6 over 0.0. That is something that is, so that is 100,000. Okay, now when you look at this again, it's 2 to the right. Since it's 1,000, right? Then this is going to be less. What is happening up? Right. Now, since the first force and the second force are in the same direction, the net just marginally distributed. 25,000 plus 10, no, 100,000. So that must give us with 100 and 105,000. Yeah, it must. Okay. Then now, question number 5 is what I want. Good. Okay, so we have a negative 3 nanocoulomb. 1 plus 10 centimeters away from this diagram below. Draw the electric pattern. So positive and negative. Doesn't matter which one we call positive. That comes first. Yeah. So, in this guy. That is that. Fine, guys, you can do whatever you want to do. As long as you see the two lines leading from the positive and from the negative. Okay, so now next we have 5.5. If there is a negative impact, then they want us to draw a force diagram showing the electric forces exerted on O by Q1. So since positive and the positive is going to be repulsed. No. The negative, the positive, so attraction. This will move in the direction. This will move in this direction. Then since it's a positive and negative, the attraction. Okay, now since they want the force diagram on Q2 alone, it's going to be then calculate the net force on Q2 as a result of that. So since we drew our force diagram into the horizontal and the vertical, I need to find those forces. If I can find the net result on this. So force horizontal Q1 over R squared. Okay. So negative 3, so it's going to be just 9 times 10 to the 9 times 3 times 10 to the negative 9, then times 4 to the negative. Distance is 10 centimeters, which I must use, which is 0.1 second. Okay. Then I just need to put that into my machine. 9 times 3, and then I'm dividing it by 0.1. 4, 8, 9, 6, 8, 1, 2, 3, 4, 8, 5, 10, Newton. Then the F vertical, 3 over R squared, 9 times the negative positive. That's it. 2 times 10 to the negative 9. This time, 35. 0, 0, 5. Okay, when I put that into the math, over 0.05 squared over 2.16 times 10 to the negative 5 meters. 10. But since the vertical and horizontal, for us to find the net force or the resultant, we said we use the vertical squared plus the horizontal squared. So I do that, square of brackets, then 8.1 is the negative plus 2.1, 10 the negative 5, but squared. Okay, I'm having 2.31. Okay, that is 2.31 times 10, 1, 2, 3, 4, 5, 5. So with the vertical, I'm getting this. With the horizontal, I'm getting this value. That's the calculator. Then we need to get the direction. We need to get the direction. So theta must be the fixed time. The vertical over the horizontal. We do the substitute. Will be 2.1 times 10 to the negative 5 over 8.1 times 10 to the negative 6. Here when you put that, gets 2.3. This is the magnitude of force. Then that has to be. Then 5.4, we have an unknown charge R. It is placed 3 meters away from unknown charge. As shown, they are telling us that the charge on R is what we need. Okay? If the net electric field is so remember what we said, for net electric field to be 0, then the electric field from different angles, let's say the electric field this side, then the electric field this side, must working in opposite direction. Can be to the left, can be to the right, as long as the direction is opposite. So we need to get electric field at P, sorry, at X as a result of P. So it takes Q over R squared, 9 times 10 to the 9. The charge is 8 times 10 to the negative 9. 10 to 6 centimeters, convert that to meters. And then when I put this into my calculator, punch that in the calculator, having 180 thou. Okay, 180 thou. Then when I look at this side, the E of X, R of X, it's gonna be K over, I'll call this R over R. So 9 times 10 to the 9 plus 2R divided by 0.01. So when I try my luck with that, because I want to try again. So 1, I'm having 9 times 10 to the that's 2R. Then remember what we said, for us to have a net of 0, must have the resistive strength epsilon in opposite direction. If I do that, it means if I take it happening in the negative direction. Okay, so that says 0 is equal to my 180 tau plus, let's say, negative 9. So move the 180 to the left, or you can transpose that, so that I have 9 times 10 to the plus is equal to 180 tau. Divide by 9 times 10 to the third. Divide by 1. And that cancels that. And then my QR divide by 9. So I'm having 2 negative. So that can also change to 9 because taking that side. Alright, so that would be that. Question number almost. Question number 6, they're telling us that two identical spheres, Q1 electron insulating stones are placed with same charge 2 millimeters apart. When Q1 is brought into contact and then moved back to original position, gain the negative 12,15, sorry, 12,5. And the charge on each sphere is this. So, guys, one thing we need to remember is that when spheres are brought into contact, there is going to be equal distribution of charges. Look at the separation. The magnitude of charges has to be the same. So number one, they want us to draw the electric field testing around both spheres after they are touched and separated. So since both things negative, so that we obtain that the quantity, which means it's just gonna be a case of 1,000. That remember the food lines have to be the same. So this we have to be centered. See, talking of a negative charge. Okay, that is that. And then 6.2, they're telling us that state the law of conservation of charge. So there are quite a number of ways you can tell us the net charge. The net charge of an isolated or an isolated the net charge is constant or is constant. Or someone can talk about that charges can neither be created, charges can neither be created nor destroyed, nor destroyed. They are just transferred. That's what happens. Transferred from one body to another. Alright, so any one of the two will work for us. They are telling us that an electron of negative, an electron, let's between Q1 and Q2, will the electron move to the left, to the right, or stay in the same position? Now they're telling us that the electron is flat. And remember we said when there's a repulsion, this area or this region of space will experience what here. Nothing is going to happen to this electron. The forces will be equal but opposite. So we're going to say it's the same position. Okay, it may be 7.4, 7.4, 7.4. Calculate the magnitude of the electric field due to the charge on sphere 0.10 millimeters to the right, 10 millimeters to the right. So if we have a point of 10 millimeters, what will be? So E, remember we said Q over R squared. So K is 9 times 10 to the 9. Remember they told us to change 7,5. Plus 7,5 times 10 to the negative 9 over the distance. They told us 10 millimeters. When you convert 10 millimeters to meters, it's going to be 0,01 square. Alright, so when I do my magic, having 67, 5,000 coulombs. Then they are telling us in 6.5 that the questions of all relate to the original charges. 1 and 4 were brought in quantity given in bold capital letters. What is the magnitude and sign of Q1 and Q4? So when we look at it, Q1, Q1, negative 7,5 coulomb. So it's a negative 7,5 plus it gained how much? It gained negative 12.5. What does this give us? Negative 7.5, that is 20. No, okay. So it is negative 7.5 gains us 1. We can write it the other way around. Okay. Same with your integer. So it has that much. Then for us to get what is left on Q4, we can do more or less the same. Where we look at negative 7.5 minus 4.5. Gaining is a plus. C is a minus. When you do that, you get a positive. That's alternative number 1. Other alternative is by looking at Q1. Yes. Divided by 2 must give us 5. If you have your Q1 known, it will be just transposing that. So that is negative 25 plus. When you multiply both sides by 2, you're going to get negative 2. This is 20, not 25. So when I move that upside, my is just going to be positive 5. Then 6.5.2, they want the force between Q1 and Q2 before they touch. So the force should say Q1, Q2 over R squared, 9 times 10 to the 9, the Q1 is 20. 5 dividing by the distance, so that's 6 millimeters. 6 millimeters is 0.3 squared. You want to put that in the 10 to the dividing by 0.03 squared, having 0.01. So that is the force that I'm having. suppose that Q1 is just since the charges are opposite, we tell us to do. So Q2 equals to 5. We are looking at this one. We are the first one. Our correct Q2 would have Q1. And then it's electric field pattern. One and before the test as well. So remember, before the test, we're having a positive and negative. And then after the test, there was a pause. So